Welcome to Stories from the NNI. I'm Lisa Friedersdorf, Director of the National Nanotechnology Coordination Office. Today it's my pleasure to welcome Sharon Walker, Dean of the College of Engineering and Distinguished Professor of Civil, Architectural, and Environmental Engineering at Drexel University. Sharon, thank you so much for joining us today. To get things started, can you tell us a little bit about yourself and how you got involved in nanotechnology?
Absolutely. First, let me start off by saying thank you, Lisa, for inviting me to participate in this podcast series. It's been one I've been following, and I'm honored to be part of a very distinguished list of folks that you've interviewed for this series. I was trained actually as an environmental and chemical engineer at Yale University, and I had the great privilege of having a wonderful mentor, Manny Elimelech, who taught me the importance of focusing on fundamental first principles in one's research. And that has provided me a framework that has allowed me to be versatile in my own scholarly career. And I really feel I need to start off by thanking him for that training. And the reason is that I was ready to jump into nanotechnology work at a time when it was an exciting new discipline, but there weren't people around yet who had had this formal training. I'd actually been trained as a colloid scientist, applying it in the area of aquatic systems, looking at fate and transport of bacteria in porous media. So it wasn't necessarily nanoparticles that were my training, but because I had been prepared to think about particles as particles and the fundamental phenomena that control their fate, I was ready to transition when the nano craze came. I have to say I was a reluctant nano person. I was a new faculty member at UC Riverside in a chemical engineering department, and I had a number of colleagues who were doing work in the nano space. And I kept thinking, oh, that's just sort of the latest craze. I'm not sure I'm going to get into that. I wasn't convinced that it was more than just a new fad. But I had a wonderful senior colleague approach me with a funding opportunity and said, look, I've created these new iron nickel composites. I'm worried that there may be some issue if they do get out in the environment. Let's look and see what we could do to study their fate. And so he would make the particles, and I started doing some work characterizing them and looking at their fate and transport using the same tools that I had been trained in from my colloid background. And it was a very exciting project because, first off, it really helped me confirm that I could use the kinds of tools and methods that I'd been trained in to analyze nanoparticles. The translation actually went much more smoothly than I thought. But I also saw in that initial project an opportunity as an environmental engineer to contribute, because in this case he was a chemical engineer who really hadn't thought about how do these particles behave in water? How do they aggregate? How might their availability evolve? Those were things that were not at all on his mind as he was developing these particles. And so that was a moment when I realized the realm of possibilities to contribute to the field. It was about that time that I was contacted by a friend at UCLA who invited me to participate in a new center that they were developing. It was the Center for the Environmental Implications of Nanotechnology, one that was funded by a combination of NSF and EPA. And I was invited to be part of that team looking at transport of nanoparticles. I was so grateful to be part of this as a participant. It was led by Andre Nell and Arturo Keller. It was a broad collaboration between UCLA, UC Santa Barbara, included faculty from Riverside and Davis, as well as other universities around the country and the world and other research labs, national labs that joined over the years of that grant. I'll tell you, as a young faculty member, being part of a center on that scale was just so wonderful and so fortunate to be part of such a team. And we had a 10-year run, which was transformative. It saw me through my promotions, through the faculty ranks, supported my scholarship and my students, and it really introduced me to a world of material scientists, engineers, industry leaders, as well as the social scientists that were involved in the thoughtful analysis of the implications of these particles.
you hit on something that we hear a lot about with respect to the NNI, and that is the interdisciplinarity. And you talked about the center that you were part of that included a lot of the UC schools and a lot of disciplines. Can you comment on your perspective about interdisciplinarity?
Absolutely. This is a discipline that has thrived, in my opinion, because people took the time to be inclusive of the disciplines. I remember early on in the center, when we had our first few meetings, it was frankly frustrating. We were all speaking different languages. And it was because of the framework of the center, it gave us an opportunity to really sit down and spend the time it took to figure out what the medical doctors meant, by what is a corona to them. Oh, you mean there's some sort of organic layer. Oh, it's over here. You said agglomerate. Oh, you mean aggregate, right? And there were these lengthy conversations just to make sure we all agreed on the semantics within the center. That was helpful. I know through NNI and supported programs and centers, there were also a series of meetings early on at that stage at the international level and the regional levels, and I participated in a number. And those also help facilitate these conversations to help bring us to a common language. Another place where we had to really all come together was even on agreement on what tools and what protocols to use. Because how a chemist might treat a suspension versus an engineer is very different. And the sort of parameters we might consider, oh, this is obvious, everyone might know how to do this. Well, but that's not going to be the case for somebody trained in this other discipline. So there was this incredible coming together of scholars to figure out how to work together. And I give NNI a lot of credit for facilitating that interdisciplinarity.
One of the challenges as the NNI was being established was the access to high-end equipment, fabrication, characterization tools in order to do this type of work. Can you share your experience with respect to instrumentation?
I had the great fortune of being part of a major national center that, although my own institution didn't have all the capacity for the fabrication and the analytics, I had partnerships. And so my students could fly around the country and access facilities. A perfect case in point is I published a paper with some images from a cryo-TEM. Well, how many people have access to that? And it was only through the center that I would have had access to that. And so what I think we see is a dividing of the haves and have-nots in our scholarly work, people who have that access and people who don't. The large centers have been quite open to bring in people, but I think that if you weren't part of a center, there were a lot of really great scholars that couldn't keep up in some of the subdisciplines because of this. And so there was, and I think to some degree continues to be, some level of inequity. Faculty that might be at a mid-tier institution doing phenomenal work, but just doesn't have access to the kind of high-level equipment. There's only so much they can do without access. However, I will say there are some real bright stars here in this story, and those are our national labs. I think that they have played a really important role in making some of this technology accessible. I actually want to call out in particular Elijah Peterson at NIST, who has been active in the community at national meetings and making himself available to help people learn about the tools. He and colleagues at NIST have made their labs available, particularly to graduate students and visiting scholars. There are cases where the national labs have really been the equalizing agent and level the playing field a bit.
So Sharon, can you share your thoughts on how the ecosystem or the community has evolved over the years?
Because of the conversations the environmental nanotechnology community had, I feel that we've evolved, that there is more of a life cycle mindset, that there's this continuity of conversation from the material scientist who thinks about how we're going to manipulate those electrons to the environmental engineer or scientist who's considering where the resting place of this particle might be if there's a release, there has been this conversation that has developed a feedback loop that has allowed for smart design. Now, it doesn't happen in every case, but because the broader nanotechnology community came together and over time has collaborated and really worked intentionally, I think we don't have that siloing as acutely as we had 10, 15 years ago. So that evolution has really been, I think, quite dramatic.
Right. So I'd like to maybe get your reflections, both looking backwards and looking forwards. What do you think are some of the most significant advancements that have been made in nanotechnology over the past 15 or 20 years? And looking forward, where do you think nanotechnology is going to have an impact in the future?
The number of advances that have been facilitated by nanotechnology is really staggering and wonderful. It's hard to sort of capture it all in an answer, but I will say where in my lens I see the biggest impacts are in photovoltaic advances. The kinds of efficiencies we see due to nanoscale materials is really exciting. And I think that the potential for even further development of renewable energy capture, storage, and utilization is very exciting thanks to nanotechnology. I think that's really going to be a game changer. And the kind of environmental and geopolitical impacts of that are, I think, even beyond what we can imagine. Closer to home in my own field, I believe that nanotechnology has really transformed the way we think about water treatment. And although we had really robust water treatment capacities before we brought in nano, we were doing great for removal of colloidal materials, bacterial, viral materials. The advancement of nanotechnology, particularly in applications such as membrane and membrane treatment, we're now able to address kind of chemical constituents that we could not before. I'm very excited to see how nanotechnology will continue to impact a number of different disciplines. In my own research area, I'm particularly interested in seeing how nanotechnology will improve our access to safe food and sufficient food supplies. I'm really excited to see how the nano-food interface evolves, allowing improvements in things like precision agriculture, sensing, and even using nanoparticles and nanomaterials to address different insect-borne or diseases in plants, for example, or in different crops. I think we have yet to see the real impact on food and agriculture that nanotechnology can bring. I think it will really help us resolve a lot of the issues around a consistent, a safe, and sufficient food supply for not just the developed world, but I'm optimistic that this can also play a significant role in making food available to all people across the globe.
Well, Sharon, I want to thank you again for taking the time to talk with us today. I'd like to give you the opportunity to share any closing thoughts that you may have for our listeners.
I think I'd like to share a particular set of thoughts for emerging scholars in our field. Don't miss out on the excellent past literature. We may not have called things nano in the past, but there is an amazing scholarship that was limited by our instrumentation to synthesize or designed at such a small scale. But there is so much to learn from the past that will help you make leaps in our new understanding with nano. There were great projects initiated that had to come to a halt because of limitations of equipment. And now you, as a new generation, can pick up that baton and really run with it. And if you afford me the opportunity to use one last idiom here, with nanotechnology, we now can operate with a scalpel as opposed to a saw. We can really look at the minute detail. But you still have to know the anatomy if you're going to be that surgeon with a scalpel. So don't be afraid to not just study the angstrom and the nanoscale phenomena. You have to back out and appreciate all of the phenomena occurring even at the broader scale, because things just do not operate in isolation. And I think that's really important to remember. And I think we all need to do that because we get so excited by what we're seeing at the nanoscale. But we have to understand how it fits into the bigger picture, because that's where our impact is seeing the connections between that nano phenomena and the bigger picture challenges we're facing.
Thank you for joining us today for Stories from the NNI. If you would like to learn more about nanotechnology, please visit nano.gov or email us at info@nnco.nano.gov. And check back here for more stories.